Good morning, everyone. Have you ever wondered why your coffee gets cold or why ice melts in your drink? Today, we are diving into one of the most fundamental concepts in chemistry temperature. By the end of this lecture, you'll understand not just what temperature is, but how it connects to the very motion of atoms and molecules around us. Let's begin with a question that might surprise you. What's really happening when something feels hot or cold? Temperature is much more than just a number on a thermometer. At its core, temperature measures the average kinetic energy of particles in a substance. Think of it this way. Imagine a crowded dance floor. When the music is upbeat, people move faster and bump into each other more. That's high temperature. When it's a slow song, people move gently. That's low temperature. Here is a crucial distinction you need to remember. Temperature is an intensive property. It doesn't matter if you have a cup of coffee or a bathtub of coffee at the same temperature. The average particle energy is identical. This is different from heat, which is extensive and depends on the amount of substance. When two objects at different temperature touch, heat flows from the hotter to the cooler object until they reach thermal equilibrium, the same temperature. It's like water flowing downhill, but with energy instead of water. Now let's talk about how we measure temperature. We have three main scales, each with its own story and purpose. First, the Celsius scale, developed by Andreas Celsius in 1742. He chose two reference points everyone could relate to: water freezing at 0 Celsius and boiling at 100 Celsius. This scale is used worldwide for weather, cooking, and most scientific work. Second, the Fahrenheit scale, created by Daniel Gabriel Fahrenheit in 1724. Water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit. That's 180 degrees between these points. It's primarily used in the United States. But here's where it gets really interesting. The Kelvin scale. Lord Kelvin realized we need a scale that starts at the absolute coldest possible temperature, or absolute zero. At 0 Kelvin, which equals negative 273.15 Celsius, molecular motion theoretically stops completely. This scale is essential for gas law calculation and thermodynamics because it has no negative numbers and represents true thermal energy. Converting between these scales is straightforward once you understand their relationships. Let me give you the key formulas. For Celsius to Kelvin, simply add 273.15. So room temperature at 25 Celsius becomes 298.15 Kelvin. For Celsius to Fahrenheit, multiply by 9/5, then add 32. That same 25 Celsius room temperature becomes 77 Fahrenheit. For Fahrenheit to Celsius, subtract 32 first, then multiply by 5/9. So 77 degrees Fahrenheit minus 32 equals 45 times 5/9 equals 25 Celsius. Temperature affects everything around us. Your normal body temperature is 37 degrees Celsius or 98.6 Fahrenheit. A fever starts above 38 degrees Celsius. In cooking, water boils at 100 degrees Celsius at sea level, and food safety requires cooking poultry to 74 degrees Celsius to eliminate harmful bacteria. Weather gives us dramatic examples. Comfortable room temperature is around 22 degrees Celsius, while the coldest natural temperature recorded on Earth was negative 89 degrees Celsius. At the other extreme, Death Valley reached 57 degrees Celsius. In science, we used liquid nitrogen at negative 196 degrees Celsius for preservation, and we have achieved temperatures within 1 billionth of a degree above absolute zero in laboratories, where strange phenomena like superconductivity occur. That's it for this lecture. See you in the next lecture.